today we're going to do systems of linear equations, which we started when we did inverses. In section 2.9 we did inverses, and in the inverse section we learned how to solve a system of equations, but it was only good if the system had just one solution. So can only find solution if it is a single point. But systems had different kinds of possible solutions. So the solution could be a single point, right? And if the solution is a single point, we could write it in vector form as a point, like that, right? And the inverse method would find that, would be able to find that if everything was perfect for it to do that. And we said it's not really efficient to do that. What other type of solutions can we have? So here's the system up here. If it crosses at a point, that means all three of those planes, because those are planes, would cross at one single point. So the planes would kind of look like a star. They would cross at one point. How else could three planes cross? Yeah, so it would be a line. So they could cross at a line. So we saw an equation of a line would look like this, which ABC is a point, so the point the line's attached to, and then the direction, which is like sort of like the slope. And then how else could three planes cross? Yeah, they could cross at a plane. And that would look like ABC. And for a plane we need two direction vectors. So they could cross at a point, a line, or a plane. And what's the fourth option? You may not have a solution. Okay. Now, the inverse method that we saw before is only good for the first case. So it's not really efficient in the general scheme of things. If you're trying to solve a system, you're not going to jump to that method because it's not going to work most of the time. So before we learn how to solve a system, using Gaussian elimination or row operations like we did last class, we're going to look at some different parts of this solution first. Okay, so how we actually solve a system. So let's say to solve a system using row reduction, called Gaussian elimination or Gauss-Jordan elimination. I actually use Gauss-Jordan elimination. They're slightly different, but I don't really tell you what the difference is. I just use one. But it's all Gaussian elimination. He sort of created the technique, and the technique is basically row reducing like we did, making ones and zeros. But the important part is knowing where to stop, because when we were doing the inverse, we knew where to stop because we were making ones on the main diagonal and zeros everywhere else. But if it's not one solution, if it's infinitely many solutions like a line or a plane, then that isn't how you know to stop. So it won't always look like that. So you have to know where to stop. So the steps are these. Step 1 is to write the system as an augmented matrix. Write the system as an augmented matrix. Okay, and we did that same first step with inverses, but we augmented it with the identity. So we put our A, and then on the other side of the line we put the identity. Here we're going to put B. Do you know what B is? Do you remember? B would be the 7, -20 here. And A is the coefficients in front of the... So that doesn't change, but we augment that. Step 2 is row reduce. Okay, so we row reduce, which is the steps that we did before, making ones and zeros, until we reach REF, which is row reduce echelon form. Now, of course, you don't know what that is right now, so that's what I mean. I'm going to show you the individual parts before we actually do one. So I'm going to show you what that is next. So, step 3. Is to identify the lead variables and free variables. So I'll show you how to do that. And then step 4 is to write the solution. And I showed you the type of solutions earlier.
Will this work on a mixed solution?
Right, this works for any of those types of solutions, so.
So if I have something that's 2 of them are crossed at a line and the third one will point.
Yeah, so the whole thing would either cross at a point on the line, or you could take 2 equations and find the line that they have in common. Yeah. But this would be for all 3, where all 3 cross.
Well, that's
yeah.
what I was thinking. You have like 2 that are crossing at a line like this.
Yeah, and the other one is, so if you have 2 that cross at a line, and then the other one splits through that line, then the whole system only crosses at a point. Yeah. So we write the solution, and that we're going to write it in parametric form and in vector form. So, and the solutions could be no solution, one solution, a line, or a plane, any of those 4 possible solutions. All right, so what we're going to start with, we're not going to go all the way through because we don't know what step 2 or step 3 actually looks like, so we're going to do them just individually to start. So REF. So the criteria to know if something is in REF is, number 1, the first non-zero number in each row is a 1. Columns containing so that lead 1, or that 1 that I talked about in number 1 is called the lead 1 or pivot. So columns containing a lead 1 have zeros everywhere else. Three, rows made up entirely of zeros are at the bottom. And four, the lead ones are in echelon form. And echelon just means staircase. And I'll show you what that looks like.
Number three, you've got at bottom.
Oh. Are at. Thank you. Thank you. Okay, so over here, just your little staircase. So what we were doing with the ones before was this little perfect staircase. The ones, if you followed the ones down, they went down on the main diagonal, and that's called echelon form when they go down. They don't have to be in a perfect staircase, but this one has to be to the left of the one in the row below it. So you could have something like this, sort of a longer staircase. But the ones still go in sort of that diagonal pattern, but they don't need to be right in a perfect diagonal, is the idea. Okay, they just have to be, the one in the row below has to be to the right of the one in the row above. So here it is one example. So this is in REF, so let's just go through the 4 steps and see why it would be. So the first non-zero number in each row is a 1. So how many rows do we have here? 3 rows. The first non-zero number is a 1. So the first number in this row is a 1. The first non-zero, that's a 0, that's okay. The first number that's not a 0 is a 1. There's no numbers that are not a 0 here, so that's okay. So that's step 1. Criteria 2, columns containing a lead 1. So I did a little square around those columns, or those lead 1s. In the column, everything else is a 0. So if we have a lead 1, we've used it and we've made everything else in that column a 0. Here's column 2, here's our lead 1, everything else in that column is a 0. And this column does not contain a lead 1, so we don't need to worry about that. This is just in columns containing a lead 1. So we only have to worry about 2 columns there because there's only 2 lead 1s. Rows made up of entirely of zeros are at the bottom. So that's there. And the lead 1s are in echelon form. This one is to the left of the one in the row below it. Okay? So I'm going to write a couple matrices down. You've got the criteria written down, so you're not going to be able to see it when I move it. I'm going to put a few down, and you tell me if they are or are not in row reduced echelon form. Okay? Okay, we'll start with these 3. So the first one. Yes or no? Yeah. The first number in each row is a 1. They go in that staircase form. That's a nice, perfect diagonal. And everywhere else is zeros, and there's no rows of zeros to put at the bottom, so we're okay. What about this one? No. So which criteria breaks down in this one? Number 2. So number 2 says columns containing a lead 1 have zeros everywhere else. Do you see it? So here's a lead 1, and that's good, it has zeros everywhere else. Here's a lead 1, that 2 should be a 0. So it's not in. So this one, yes. This one, no. You're not done reducing. Yeah, so you'd have to then say, oh, shoot, that 2 has to be a 0, and then you do the step to do that, which we actually learned last class, the steps to make the zeros. What about this one? No. Which criteria breaks down? 4. The ones are not in echelon form. So these rows should be switched, which is just one row reduction step. Switch the 2 rows and then you're okay. So this one's no. So this one was number 2, didn't work, and this one was number 4, didn't work. Okay, so let me write a few more. Nope, because there's no row entirely of zeros. Right, so okay, so 4, what do you think? Yes. 4 is yes. The ones don't have to be in an exact diagonal, but they do have to be the one in the row below. Any rows of zeros are at the bottom. There's a lead 1, zeros everywhere else, a lead 1, zeros everywhere else. That's good. Here. No, what's wrong with it? Yeah. So you could argue 2 things, but what I want to point out is that after the line doesn't matter. So when you're looking at row reduced echelon form, you actually don't care about this stuff. Okay, so now ignoring that, is it in row reduced echelon form? It actually is. So there's a lead 1, and everywhere else in that column is 0. These are both rows entirely of zeros. That 3 doesn't matter, because you never do any row reductions on the answers, right? So this one is okay. So yes, this has a 1 here, but it's not a lead 1. The only lead 1 in this particular example is right there, because of the first non-zero number. So this one actually is yes. So I wanted to point out that you could have argued that it wasn't because rows of zeros have to be at the bottom, but they're actually both rows of zeros, and we don't really care what's here. This is an example of no solution. When you get zeros, and then this is like an equal sign, so 0 equals 3, which is not true. So that one actually has no solution. This one. Yes. The 2 looks funny to people, but the 2's okay, because the 1, everywhere in the column has to have zeros, and the next lead 1 is right here, and everywhere in that column has to have zeros. This 2 is okay because it doesn't have a lead 1. So numbers are okay, and it just, if they have a lead 1 in that column, they're not okay. All right. Okay. So, and we'll see more when we actually do examples, but that's the idea, okay? That's what REF is. So the next is how to write a solution. Oh, thank you. So you stop row reducing when you get to the right form, but then you have to take the numbers out and be able to write the solution in vector form and say whether it's a line, a point, or a plane. Okay, so that's how we're going to do, what we're going to do next. So I'm going to write a row reduced system, so just at the very end. Okay. So when you look at this, you've stopped here. This has 3 variables. These were the x's, the y's, and the z's. This was your equal sign in your system and the answers. So the same way we put them in, taking the x and the y off, we put them back. So this, how many x's are here? 1. How many y's? None. And z, none. Equals 2. So this just gives us x equals 2. And the second line has no x's or z's, but just one y. So y equals 3, and z equals 5. So this is an example of 3 planes crossing at a point. And we can write the point in vector form. Okay. So this is a point. Okay, number 2. So this is still the same size system. We had 3 variables, x, y, z, and 3 equations. And you still take it out the same way. But what we do first, before we write the solution, I said the steps were identify the lead variables and the free variables, and then write out the solution. So I didn't do that here, but anytime you've got rows of zeros or anything that's not perfect, like this one was perfectly reduced, one's down the diagonal, zeros everywhere else, you need to identify what the free variables are and the lead variables. That's really easy to do. Anything with a lead 1, so x is a lead variable, and there's another lead 1 here, so y is a lead variable. Anything that does not have a lead 1 is called a free variable, and that's going to give us our t. So one free variable, because this has no lead 1, one free variable is going to be what type of solution? A line, right? So a point has no free variables. A line has one free variable, that's the t. And a plane has 2 free variables. So here we've got one free variable. So we still write out the solution the same way. This is x, but then there's 2z. So this is x plus 2z equals 3. And our second line gives us y equals 2. Now our solution, remember, is x, y, z. equals. Okay, so we need to have an answer. Let's start with the parametric form. X equals Y equals Z equals. So parametric form. And this will be vector form. All right, so here's our equations. The only thing I can put in right now is that 2. Now, what do you think for the other one? So what you're going to do, we're missing the Z, but we said the Z is free. So any free variables, you give them a letter. T, R, there it is. So if Z is T, then what's X? All right, 3 minus 2T. So you would rearrange this. Rearrange. So you'd have X equals 3 minus 2Z, but Z is T. And that's what you would say, 3 minus 2T. See how it works? So, if we write this out as a point plus T times our direction vector, so for the point, you look for the numbers that do not have a T. So a 3 doesn't have a T, a 2. And what about in the Z? 0. So 3, 2, 0. So that's our point. And then our direction vector, we've got a minus 2T, no T, so 0, and 1. And so that would be vector form. So the systems that we're solving don't have to be size 3 by 3, like a 3 variables and 3 unknowns. This one has 3 equations, but it's actually 4 unknowns. You see there's 4 columns. So instead of X, Y, Z, we would usually call these X1, X2, X3, and X4, like that. Okay, so this actually has 4 variables. So first of all, I'm only giving you ones that are row reduced. You might think it's not row reduced because of the 2 and the 3, but why are the 2 and the 3 okay? There's no lead 1 in that column, right? So that's going to be your free variable. So the lead ones are here, lead, here, and here. And this is in 4 dimensions, so we're not going to say it's a line, but it has 1 free variable. Okay. So when we write out our solution, what do we get for the first line? X1, 2x3 equals 4. Our second row, we get x2 plus 3x3 equals 5. And our last row, x4 equals 6. So since our free variable is x3, x3 is going to be t, you plug that in and you rearrange them. So you would put this in here and in here where there's an x3. So x3 is t, so you'd say x1 is 4 minus 2t and 5 minus 3t. So you just move that free part over to the other side. So our solution in parametric form So our free variable was that one, x3. x4 was just 6. And we have 4 minus 2t and 5 minus 3t. And in vector form, so what would we have in vector form? So you look for the numbers that don't have a t. So 4, 5, 0, 6. 4, 5, 0, 6. And minus 2, minus 3, 1, 0. Yep. So let's write one with 2 free variables just so you can see what it looks like. So 4. Okay, so number 4, how many variables are there? So variables 1, 2, 3, 4. Which ones are our lead, and lead? They're the ones with the lead ones. And don't just look for ones, because there could be a number that's not a lead one. It has to be a lead one, the first number in each row. And then the other 2 are free. So we could call that one T and this one R. All right, give them a letter. So we have, if we take this out, we would have x1 plus 2x2 plus 3x4 equals negative 2. I think the x3 is missing. And our second row, x3 minus 3x4 equals 4. And the third row gives us nothing. So remember that x2 we're going to call t, and x4 we're going to call r. So we would put the t's and r's in here. So this first equation will give me x1 plus 2t plus 3r equals negative 2. And you solve it for x1. So what would x1 equal? Minus 2 minus 2t minus 3r. And then do the same thing here with x3. So x3 minus 3x4 I called r equals 4. So x3 is 4 plus 3r. All right, so we've got all we need. Your solution, always put it in order. There should only be an equation here for anything that had a lead 1, and the others should have either a number or a T or an R, something like that. So T, R, and then we need an equation for the other 2. So x1 we said was minus 2 minus 2t minus 3r, and x3 we said is 4 plus 3r. So we've got 2 free variables. So look through any numbers that don't have a variable, which would be in your point. So negative 2 in x2, 0, x3, 4, and x4, 0. Now we look for the t's. So in the first one, negative 2. In the second one, 1. The third one, 0 and 0, no t's here or here. And then the r's, -3, none, 3, and 1. So that would be your vector form. Now, it's not a plane because it's in 4 dimensions, so there's no physical representation when we're in 4 dimensions, but the same idea would apply if we had just 3 variables. Okay, so that's basically the idea. We'll see more solving them, but that's the idea that we would see once we get to the end that we need to write down. Okay, so what we're going to do next is actually solve a system. So we'll do that in the next video.